Welcome to this deep dive. Honestly, what we're talking about today is going to blow your mind. What kind of God-tier networking innovation can turn exascale level, yes, gigascale AI factories into reality? Get ready to lock in because we're going straight into the hardcore breakdown and show you what powers modern AI computing at the foundation and what it really looks like. All right, let's jump right in. Today's roadmap is very clear. We'll start with a layered cake structure of AI factories. Next, we'll look at 4 major network architectures, how to beat network jitter, the latest breakthroughs in optics and storage. Finally, let's look at how engineers use simulation to build future infrastructure. The core idea running through everything today comes down to one thing. The data center itself is a computer, and the network determines what it can do. So this line is really important. Just think about it. No matter how insanely powerful a single GPU is, without an ultra low latency network to connect them, then they're just isolated islands, no chance at all. To put it simply, the network is the nervous system of this supercomputer. To make it easier to understand, let's imagine a layer cake. At the top layer are the apps and big models everyone knows. Going down is the strawberry flavor infrastructure, then the chocolate flavor compute chips, that is the GPU and CPU. And at the bottom layer is the vanilla flavor power. What we're discussing today will focus entirely on the physical foundation, the energy that supports it, all the chips, and that absolutely essential infrastructure. Now that the focus is clear, let's move into Part 1, building AI factories. The 4 essential network architectures. There are 4 main tasks here. First, scale up, that is scale up linking multiple ASIC GPUs perfectly in sync as one compute unit. Second, scale out responsible for linking together more than 100,000 GPUs. Third, cross-site scaling, also known as scale across. Now this one is impressive, used to connect data centers 10 kilometers apart. Finally, the infrastructure that supports context, memory storage. Here, I need to point something out. When transmitting over long distances, it still has to avoid the latency penalty caused by traditional deep buffering. This is a true nightmare level engineering challenge. Speaking of challenges, we have to mention the ultimate villain in the AI factory. That's what we call network jitter. Jitter. In AI networks, even microsecond level delays can cause a disaster. It can leave a full 100,000 GPUs just sitting there waiting around. Exactly. If even one packet is late, the whole system just comes to a stop. And what gets burned isn't just compute power, but an enormous amount of time and money. So here's the key part. Now let's move into part 2 and take a look at Spectrum X. How does it completely defeat the network jitter villain? You see, traditional Ethernet was originally designed for single server tasks. It relies on deep buffers, and it can tolerate jitter pretty well. It handles normal cloud workloads just fine, but the moment it faces distributed AI workloads, these monster scale jobs, it falls apart. By contrast, specialized systems like Spectrum X AI Ethernet, built from the ground up, was built for distributed computing from the ground up, not only doing zero buffer copies, but even more impressively, it achieves true zero jitter. The whole process is like an incredibly elegant duet. Step 1, the switch performs unconditional global load balancing. It isn't rigid. It dynamically finds the perfect path for every packet. Then step 2, the endpoint SuperNIC takes over and precisely handles data reordering. Step 3, directly push the data into GPU memory with no wasted effort on extra copies. And with telemetry data collected by the Sony system, it could even act as if it had opened its heavenly eye and get ahead of network congestion before it happens and handle it. Next, this number will absolutely surprise you. 14x. You heard that, right? Thanks to this tightly integrated hardware-software design, users only need to update the software on the exact same hardware setup, the supercritical networking performance into a massive 14x gain. This is the infrastructure built for AI that gives it its confidence and magic. Once you understand the network architecture, we'll move right into part 3, optics, power, and storage. Let's talk about data centers and the physical constraints they can't escape, namely the brutal power budget and the critical transition from copper to optical technology. Copper is actually great. It's very reliable, low latency, power consumption is almost zero. But the downside is that once you go beyond the rack, the transmission distance is painfully short. So To solve long-distance scaling, we have to bring in co-packaged optics, also known as CPO. It uses liquid cooling and directly integrates the optical engine with the network switch chip package. That not only greatly extends transmission distance, it also cuts the number of laser components by 4-fold. This lets us scale up without blowing the power budget. But what's really interesting is this three-pronged 5-fold performance boost. First, the CPU has a closed design reducing human contact and physical wear, directly boosting the AI factory's uptime by 5 times. But that's not all. If paired with the new Bluefield storage infrastructure built specifically for inference, we also achieve a 5-fold increase in token throughput and 5-fold energy efficiency, a total win-win-win with hardware specs. This crazy we come to part 4, simulating the AI factory. You know what? If you were to build one in the real world by hand, a data center worth $1 billion, the risk would be unimaginable. One tiny misconfiguration could leave tens of thousands of pricey GPUs just sitting there idle. The traditional way to verify and debug a data center can easily take months. But now, with the DSX simulator, this digital twin, we can spend just a few weeks in a virtual environment, booting up and testing all the software. And the best part is, as long as the simulation runs perfectly, engineers can copy and paste the parameters with one click into the real infrastructure and get deployment done in just a few days, guaranteeing it works perfectly the first time it powers on. Finally, we've reached the last 5th part, topology scale. It sounds pretty academic, but the concept is actually super simple. How the physical cables are routed directly determines the ceiling for AI compute. This comparison perfectly shows how big a difference changing the topology can make. Look at the traditional 2-tier single rail setup. Its limit is about 2,000 GPUs. But if we switch to a multi-rail design, meaning based on the GPU's actual communication patterns, we force traffic to be split across different switches. The network capacity instantly jumps by a full 4x. With exactly the same number of tiers, it can directly support 8,000 GPUs. It's like taking a road that's already jammed to the limit and magically building several elevated express lanes on top of it. Ready to see something even crazier? We're not stopping at multi-rail. We're also adding multi-plane evolution. By baking hardware-level load balancing directly into the SuperNIC, we can let 8 independent planes handle traffic at the same time. When this technology is stacked on top of the 4-rack design I just mentioned, the miracle happens. We can actually, in a mere 2-tier network architecture, push the scale all the way to 500,000 GPUs. And its system resilience is absurdly strong. Even if one switch suddenly dies, bandwidth only drops by 6%, and the whole system keeps running smoothly. It doesn't crash at all. But here's the problem. How do you maintain a network this huge? The answer is amazing. Use AI to take care of the infrastructure. Let me share a real-world example that's incredible. The AIOS system is like a super detective. It does this by quickly analyzing the massive telemetry data from a gigascale AI factory. It literally found a needle in a haystack. With pinpoint accuracy, it identified the only damaged physical cable. This fully proves that AI already has the ability to automatically monitor and maintain its own nervous system. All of this has truly, completely reshaped our vision of the future. Just imagine when our network infrastructure can perfectly synchronize 500,000 super GPUs, making them run like one giant super brain with zero latency. What limits will there even be to the intelligence we can create? I hope today's breakdown helped you see the shape of future computing. Stay curious, and I'll see you next time.